Well, hello friends. Welcome back to the program. Today we are going to work on performance in SerenityOS, and I have a little thing I want to investigate. So the backstory is that in the last week or so, I've been working on the stability of our continuous integration system and just fixing random kernel bugs that were causing test runs to fail. Despite no new failures being introduced, we had like kernel bugs that would just crash the CI runner. So we've gotten to a pretty good place with that, which I'm really happy with. And in the last week while working on this, I've been reading a lot of our CI system logs, and I noticed something that, let me just open one up here. Hello. That some of our tests, like especially these shell tests, are taking a very long time to run. Like look at this valid.sh, takes 14 seconds, subshell 13 seconds, immediate.sh 16 seconds, and so on. These are pretty long times for what are essentially simple shell scripts. And let me show you what these look like if I run them locally. So for example, this one here called control structure as command. Yeah, it runs pretty fast, right? Now, of course, there's a big difference between my machine and the machine that we get assigned by the GitHub Actions test runner. My machine is much faster, and my machine supports hardware virtualization. So let me go ahead and turn off hardware virtualization so that we get a little bit closer to the test runner used by CI. Of course, it will now take substantially longer to boot this machine, but I think the result will be more interesting. My local machine here, of course, is still a much more powerful machine than the random bot we get on CI, but it should be at least a little bit closer. Okay, yeah, so it's quite a bit slower than with hardware virtualization, obviously. So now it runs in 4.6 seconds, and it's nothing compared to 32.8 seconds on the CI, but still substantially worse than 300 milliseconds or whatever I got with hardware virtualization. So what we're going to do today is try to improve the situation, I guess, by profiling and finding out random things that we can improve to make this go faster, and see if we can learn something interesting along the way. And I've been meaning to look into this for a long time, but I kept postponing it because I don't know, you just postpone things sometimes, I guess. But now we're going to look into it. So here we go. Let's grab a system-wide profile. We'll run the command. And of course, we're grabbing a system-wide profile with hardware virtualization disabled so that we get something more closely approximating the CI situation. If we were to run it with hardware virtualization, we would get a much shorter profile with fewer samples, so it would probably be less interesting. So I'm just going to reboot Serenity with hardware virtualization on so that it's fast, because I'm going to browse around the profile and stuff, and I would like it to be fast. So what do we have here? A bunch of programs were captured. So we have all of these shell processes, I guess subshells, and then we have a bunch of various command processes. This looks like pretty typical shell script execution. Let's actually bring up the script that we were running just so we can look at it. what was it called? Control structure as command. Yes. Okay, so it is a shell script that has some shell scripty stuff. It has a for loop here, but essentially it's running a bunch of executables, right? That's what a shell script does. Shell script is all about forking and execing executables with interesting commands and output input redirection stuff. And that's what we see here. A lot of different commands. And I guess the first thing that stands out to me is that echo is run as a command and not as a built-in. Echo, which echo? I would have thought that we had an echo built-in echo. I guess we don't. So that's probably an area where we could improve. But it feels like echo built-in for shell. It feels like a kind of a hack specific to this benchmark, right? It wouldn't be a generally useful optimization. It would only be useful for things that happen to do echo. But even so, it is an idea. And then what else is going on? Because just on that echo thing, I think Bash has a echo built in. Yeah, they do. So we could have one too, I think. And that would save us the trouble of a fork and exec just to echo stuff, which would get rid of at least some of these processes here. Okay, and man, there are so many of these little guys. So let's, and we have quite a few samples in each one of them. So I guess we can look at what they actually do. Let's get an inverted tree. And we see that most of them are in the kernel, doing region mapping within mmap, called by the dynamic loader, as at least what this echo is doing. So let's look at this deer name right here, top stack, mmap, called by the dynamic loader. Okay, so that kind of makes sense that all of these little programs, they're all dynamically linked, which means that when you start them up, the first thing they have to do is go and find all of the libraries that they depend on, like libc and so on. And that's going to take some time. So possibly even more time than anything else the program does. So that's definitely an area where we could probably improve. Dynamic linking on startup needs to improve. But how? How though? How do we improve it? And then we have Windows servers at the top here. And this actually is not at all representative of a typical CI run, because on CI, we don't start in graphical mode. So we don't have Windows Server running, whereas here it just dominates the profile. I guess we could approximate the CI better by starting in text mode and profiling that. But we can also just disregard Windows Server. And here is our, and of course, same thing goes for the terminal processes, which also are not present in the CI run because it just runs on the text console. But we're more interested in what the remaining processes are doing anyway. So this is our most active shell process, which again spends most of its time in the kernel behind a spin lock. So there's the issue with spin locks in the kernel that once we take a spin lock, we enter into a critical section. And while we're in a critical section, we are not able to sample the process. So we can't actually make a recording of what it's doing. So this is what it looks like when you were capturing samples, when you were sampling for profiling purposes while a spin lock was held. Then it just looks like this, like you see the destructor of the spin lock locker and all of your samples are collected there. We can see that munmap is, I guess, very heavy in this shell process, and it's being called by the dynamic loader, load program headers. Load program headers, which calls munmap on a reservation. Wait just a minute. Okay. What's going on here? We make a reservation. Oh, yeah, right. We make a reservation of virtual memory when we're gonna load a library or a shared object of some type in load program headers. We try to make a VM virtual memory reservation that is the full size required by that library, and this is just in order to flush out any VM allocation failure. So if there wouldn't be enough VM to load this thing, then we can just fail early. Because we need a single piece of contiguous VM. And then we create that mapping, and then we unmap it immediately after it succeeds. And then what do we do with the reservation? Then we use the reservation as a base for subsequent calls to mmap, one for each region that we're mapping. Okay. But this munmap here in load program headers is the single heaviest thing going on in the kernel in this shell process. So why is that so heavy? I guess in the region destructor is very heavy here. What is the region destructor doing? Okay. So let's take a look. The region destructor takes the spin lock, sure. Okay, so it takes the spin lock here, and then we don't see what's going on. Actually, let's flip this view around from not inverted and switch to top functions, and then maybe we can view it the other way around. So syscall entry, and we want to look at munmap. Okay, so here's the region destructor, and it destroys various things, but by far the heaviest part of this destructor is what's behind one of these spin locks here. So unmap, basically unmapping the region. Sure. And what unmapping does is that it will update the page tables so that they no longer point to the underlying VM pages of this region. And this other stuff, this is registering the region with the underlying VM object. You take a lock, remove from regions, which is an intrusive list, I think. Yes. Then you unregister the region. Which removes it from the kernel regions. Is that a red black tree? Yes, it is. Okay, well, one thing immediately stands out here, which is that we are taking a spin lock even if it's not a kernel region. So this could probably just be reorganized like this at absolutely no disadvantage, or like there's no reason not to do it that way, because if it's not a kernel region, then we don't care. This thing only tracks kernel regions. So in our case, when we're doing the dynamic loader thingy, these are all user space regions. So that means that we can avoid taking that lock at least. Yeah, that seems worth doing, like not taking a spin lock. So let's see, let's go ahead and just commit that change right away. Don't take spin lock unnecessarily in region registration. Since we only care, actually, you know what? Let's do this slightly better. If we only care about kernel regions, we can also only call it if we are a kernel region. So we could even do something like this. If is kernel. Yeah, this is way nicer, because then we also lose the function call in some cases where it's not relevant. Okay, this one, I mean, this is a small thing in the great scheme of things, but it's also like kind of a simplification, which I like. So let's go ahead and do it. And then here we can just verify these things instead. Okay, I think we should be kernel only register kernel regions with memory manager. This was essential. This was already, well, we were already only tracking kernel regions. This patch just makes it more clear by having it reflected in the name of the registration helpers. We also stop calling them for user space regions, avoiding some spin lock action in such cases. Yeah, I mean, that's just a better way of doing that, because taking less locks, obviously better. Okay. So what else is going on though? Dynamic loader, where was the mmap? Here's mmapping individual subparts. mmap with name. Right. Wait, what am I looking at now? Oh, this is when we create the dynamic loader. Right, so in this case, wait, why is this private? Why am I making a private mapping? Because this mapping, like when I'm just interested in like reading the header of the elf. I think that could just be a shared mapping, because it's a read-only mapping anyway, so why make it private? That just prevents us from sharing it. Okay, do I have all the information I want from here? I mean, I guess I can. I can make a new profile. Yeah, that's fine. Just want to validate that it still boots if I use a shared mapping, because this data mapping here, so we make a mapping when we load any dynamic object, just so that we have a place to read the header from, the elf header, and to like copy data segments and stuff. And it seems to start up just fine without that. Where does this end up? Dynamic loader. Where's the constructor? That's the data right here. It goes into file data. And the destructor just unmaps it. Sure. Yeah, so it's not used for anything other than, I think it's not used for anything. File data. We use it to construct the ELF image parser. Sure. We use it to validate the ELF header. We copy data segment content from the file data and the TLS data, which we then copy from as well. Yeah, so it's just a read-only copy. It could totally be shared. Don't know why it was like that. So libelf map, use shared memory mappings for when loading ELF objects. There's no reason to make a private read-only mapping for just for reading and validating the ELF headers and copying out the data plus TLS content, data segments. Yeah, I wonder if that affected any of these things so far affected the runtime of the test. So far we're just doing like obviously good ideas. Tests, shell, control structures. Oh shoot, I have to, of course, disable the KVM thing. But this mmap, this was not the heavy mmap that we were seeing. The heavy mmap was the one in load program headers, the reservation thing. So the fact that we map and unmap immediately, and this one is the heaviest one, that tells me that there's probably something we can do smarter here. Because all of the mappings that we're setting up here, then we just throw them away. So clearly there must be a way to either to express more clearly to the kernel what we want to do. Like if we had a separate syscall, like, you know, like Serenity VM reserve, that would take sort of these two inputs and it would just reserve that VM space in our range allocator. Or perhaps better would be if we could find a way to sort of detect what's happening here in the kernel and make the kernel avoid doing the work or avoid doing so much work for it. Just checking if we improved dramatically. It didn't really feel like it. So like 4 seconds or something, 4.2 seconds, yeah. All right. Yeah. So let's see, we're making a prot non-mapping. So none of these, it shouldn't actually have any memory backing it. Which I guess means that why would we don't even need to create mappings actually. Because what's the kernel supposed to do? Like all we really need to do in the kernel in response to this mmap is to reserve a chunk of virtual memory. And also, I guess, commit a number of memory pages. But outside of that, like, we don't need to change the page tables at all. I think. So can we just avoid updating the page tables when this happens? How will that work? Because, let's see. So if the reservation doesn't update the page tables, that means that the unmapping of this reservation also wouldn't need to change the page tables. So you could avoid updating the page tables for both of these syscalls, which I think would remove a substantial amount of work that we're doing here. Let's see how that would look in practice, though. So let's see. This is anonymous memory, right? Reservation mmap flags. Anonymous, sure. So it's anonymous, and we create a VM object, and then we try to allocate it a region with that VM object, sure. And blah, 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 check. Create the region, add the region, and then we map the region. Should flush TLB? No. Right, so we're already smart enough to not flush TLB caches for new mappings because the CPU does not cache absent pages in the TLB cache. So you only need to flush TLB if you are removing mappings or decreasing access rights to a mapping. I think if you're adding new mappings or reducing, reducing restrictions on a page, then you can just not update the TLB, and then you can get like a spurious page fault or whatever that you just ignore. But what if we just did nothing? Do we have the prot here? If prot is prot none, which means that we don't need to do anything. So wait, now I didn't do it right. If prot is not prot none, if prot is not prot none, then we set up the mappings. But if it is prot none, why do we need to set up mappings? Does it do anything else important? Probably something. Let's test it. Okay, well, we panicked on boot because mmap non-writable file already exists. Okay, so what does this thing do that I stopped doing now? So we take some spin locks. This is just some sanity checks. Set page directory. Oh. So we're setting, right. So we're attaching the region to the page directory, which means that the page directory is now aware that this region owns some of its virtual address space. So I guess that might be where we're falling apart. So maybe we have to, let's see, added region set page directory. We probably still have to hook that up. Page directory like that. Okay, now we have a new panic. Panicking because in region set page directory, we are asserting that, that we're holding a lock. Sure, that makes sense. So we have to hold the mm lock. Well, I guess we can just take the mm lock, whatever. Let's take the memory manager lock and try that again. Let's see, so what are we doing here now? We are essentially not mapping prot and unmappings into the page tables. And seems to not fall apart, at least. Wonder if it's any faster. Well, sub 4. Doesn't seem like crazy faster. Perhaps a tiny bit, but maybe the real payoff comes when we change munmap, because munmap was where we saw like the most time spent in that profile. So unmap mmap range. Let's see, so we're unmapping a whole region, which means we call deallocate region, which calls take region, and then just voids it out, which means that we end up in the region destructor. And we end up here in unmap. We're calling unmap. Right, this is where we were losing all that time. So let's see. How do we know that we didn't map anything? I guess if we are prot none, right? That means that we don't have mappings. So let's say that if oh, there's no prot stored. Well, we can just compute it, right? Like this, like if not readable, not writable, not readable and not writable, and not executable. Then do nothing. Wait, does that make sense? Because then we never mapped in the first place, which should mean that we don't need to do this. Also, unmap, like we take these two locks here, and then unmap goes and takes those two same locks again, which means that we could probably make that better. Okay, so what doesn't work now? File already exists. mmap non-writable file already exists. Okay. Is there something else that happens in unmap? Oh, yeah. We have to deallocate the VM. Unmap takes care of deallocating the VM. That's kind of a weird responsibility that unmap has, actually. But let's maybe not try to fix that right now, but rather we'll just take care of doing that here in the do nothing case. So here we'll deallocate the VM. And I guess that means that, that means that in either case, I have to lock the page directory. So I can actually move that up here. Okay. It takes a moment to boot up. Let's see. So the first run is cold, but ooh, look at that already. Already cold, 3.7. That is definitely an improvement. Okay, 3.8. 3.6. Look at these times. So we're looking at potentially about like up to 10% time reduction from not creating these mappings for prot none. So basically, the dynamic linker, creates a prot none memory mapping and then throws it away. Just to the whole purpose of that is to verify that we have that amount of contiguous VM at a specific address that we're interested in, or anywhere if we're not interested in a specific address. And yeah, so my first idea was to add a special syscall that just creates a reservation and then discards the reservation. But I guess having a more generalized solution to this means that anybody can take advantage of this optimization. You don't need to be aware of the special syscall, right? So if you create a prot none mapping, we don't go through the trouble of setting up page tables for you. We'll do that later if you and protect it or something like that, right? So that feels like an improvement, although we're going to need some comment here to explain what's happening. Also, I guess we can just simply call unmap with locks held here. Wait, and then we have to pass in should flush TLB. Yes. Page lock Okay, let's just name these same as the parameters. Okay. Yeah, okay, so how do we explain this? If the mapping, the region is prot none, we didn't map it in the first place. So all we need to do here is deallocate the VM. Yes, and then we have a corresponding comment, I guess, in, where the heck was it? Address space.cpp, prot none. Maybe we should reorganize this code so that it reads like this instead. Prot none mappings. We don't have to set up any page table mappings. We do still need to hook up the page directory. Attach the region to the page directory though. Yeah. Well, this is just straight up pleasant. Very cool. Okay, let's get a profile and see what it looks like now. Okay, and let me just exit out and boot up again in fancy hardware virtualization mode. Yeah, I mean, it's still very fast in hardware virtualized mode. Okay, so what does this look like now? Now, the top thing in the top shell is fork instead of unmap, munmap. That's very cool. Great. So now fork is the big thing, followed by page directory construction, followed by region map. And that's mmap in where exactly? Dynamic loader, try create. Sure. Sure, that's fine. Okay, what about all these little programs? mmap, dynamic loader, try create. Oh, I guess when you are mapping an... Yeah, that's obviously not prot none, so we don't get any benefit from that. When you're mapping like the entire inode. So I guess we still want to do that. I'm just thinking, like, what are we actually mapping when you're setting up an inode mapping like that? Inode file mmap. We do process address space, allocate region with VM object. But this one will be like prot read or whatever. And it will be prot read, so we map it. But could probably find a way to avoid work here also. And make those mappings lazy so that like you allocate the VM, but then you just leave it as and then the next time we get a page fault, then we can create the page table mappings at that point, sort of lazily, I guess. That would be an option, but that feels like a larger refactor that I'm not going to dig into maybe right now. Because I'm already kind of happy where we ended up here. Like almost 10% is a very, very nice catch, I would say. So what do we have here? mmap, try create, sure. Okay, so all these little programs still in mmap. I guess that's fine. I wonder what is terminal doing though. Pull. Windows Server. Oh, Windows Server is just mem copying like nobody's business. And polling. Okay. Fork. Fork is something that we've always known to be heavy. Wonder if there's something like obviously goofy going on with fork. I guess we can turn around the profile and see if we can peek into it. Fork, process, try create, and then spin lock. An address space creates a page directory, which is heavy. Why is that heavy? Page directory, try create. Most of the time is spent while holding a spin lock, sure. So we're holding the spin lock and then we allocate physical pages and We also, let's see, set up page table mappings. I mean, the page table mapping stuff is always a bit heavy, for sure. Because we don't keep kernel page tables mapped normally. So you have to take, if you want to mutate page tables, you have to take the memory manager lock, map the page table somewhere, and then poke into them. There's probably ways we could make that faster. What else is it doing? Virtual range allocation, sure. Cloning the thread. Probably like allocating a kernel stack for the new main thread, stuff like that. You know, let's unmask the spin lock here in sysfork, because I remember I've done this in the past where like you just go here and like don't take the spin lock and see what happens, and then obviously this is like not correct, but maybe it can give us a little bit more insight into what's going on, as long as we don't trip up some nasty race. We might be able to get away with it. Let's see. Okay. Oh. Okay, and then let's open that up in a fast emulator. Okay, so let's take a look at sysfork. Okay, so now that the spin lock isn't taken, we can actually see what's happening here. We see that most of the time is spent below region try clone and region map. Okay, region map, that's another one, making page tables. So there's another opportunity, I guess, if you're forking a process that has unmapped regions. So here, right, if child region, if it's not readable, child region is not writable, and child region is not executable. You know what? I'm just gonna let's just log something to see if it actually happens. Hello, fork with prod none region. Lol. Yeah. We'll catch that one next time we run. See how many there are. Okay, and then we have region try clone, which does VM object try clone, which we can't see into either. I bet you we could probably do something about that. K-string clones. Yeah, we're cloning the name of the region. When you clone a region, obviously we have to clone the string with the region name. Unref. Wait, why do we have an unref? We should never unref a region We should never unref a VM object when creating a new region clone. So why is that happening? Okay, this is a copy. Here this is a ref copy. This is, we make a clone of the VM object and then we pass it as a, we pass it as a copy to this function here, which means that this thing will eventually go out of scope and do an unref. So we can totally avoid that unref by doing that. Ta-da! Move semantics to avoid one unref. But let's do it. No reason not to. Was it here? Yeah. Kernel. Use move in region try clone to avoid a VM object unref. Yeah, I mean, come on. That one, we're not using that afterwards, right? Yeah, no, it's not used later. Okay, so let's, I guess, run again and see if we can see that red text that I added if you have fork with the prot none region being cloned. And we should see a bunch of red. Oh, look. One red during boot and not a single one during the test. So that's probably not the most common thing that you fork while having prot none regions. So I'm not going to sweat that one right now, I think. But let's at least commit these other two things that we did. So kernel, don't bother, don't bother with page tables or prot none mappings. When mapping or unmapping completely inaccessible memory regions, we don't need to update the page tables at all, since there's this saves a bunch of time in some situations, most notably during dynamic linking, where we make a large VM reservation and immediately throw it away. Yeah, that's really, really nice. Okay. And that little move here was nice as well. And then I wanted to look into the VM object try clone, this guy right here. I guess the anonymous version of that takes the spin lock. Let's just not take the spin lock, see what happens. Although I'm not sure what we can do in there, but maybe something stands out. So I guess really what we're doing now is like looking for low and medium hanging fruit instead of more like architectural rethinks. But I think that's okay. I'm sure we have lots of low and medium hanging fruit, stuff that I'm not even thinking of right now. You got to start somewhere. Hello. Okay. Oh, dang it. I actually wanted to capture a profile. Yeah, but I feel like I'm getting towards the end of the video because I'm happy with the bounty that we have collected so far, and no need to push it. Gotta leave something for our future selves. So let's just grab a last little peek into wait, what was it called? Tests? Yeah, I want to look into anonymous VM object cloning as well, just to see if there's something that stands out here as nonsense. Can't hurt to look, but actually, there we go. Fork, try clone, anonymous VM object try clone. Okay, so that one does calls the constructor, which calls the base class constructor, which does a kmalloc, which takes a bunch of spin locks. Just spin locks everywhere up in this house. Guess it's this constructor here. Yeah, which calls this base class constructor, cloning the set of physical pages, and then registering the VM object with our global list of all VM objects, which is kind of unavoidable, I guess, because we... let's see. It's kind of an architectural issue. I guess we could avoid doing this if we had a different way to reach them. So if instead of registering all VM objects individually, they would instead be registered with an address space, for example, or with some other entity, and then you could walk them that way. But that doesn't feel like the end of the world, the fact that you have to add it to this instance list. Okay. Yeah, nothing stands out as like obviously terrible here. So this probably need a little bit more brain activity to come up with some optimization ideas. I guess one thing that's a little bit weird is that when we fork, then we're creating a new address space, right? So the new address space we've never executed in the new address space yet. So the first time we switch into the new address space, we will activate its page directory for the first time. So there's no caching to worry about. But when we clone a region, then we have to remap the source region that's being cloned in order to make it copy on write. Which means that if we are turning on write protection, then we have to remap it in the parent, which I guess is what's happening here. Try clone, remap. Try clone. Calls remap, set up a cow region. The parent, this region becomes cow as well. So you unconditionally remap, but What if we're already write protected though? That just makes me curious. What if we are, if we're not writable, then we're remapping ourselves to be non-writable for no reason? I just want to, let's just find out if that happens. This is how I like to find out if things happen. XXXXX. Hello there. Huh? Do a little bit of Obi-Wan debugging. Yeah, because if we are remapping already non-writable regions just because we make them copy and write, then we are totally wasting time on that. But I don't know if that's actually happening. We'll find out. Well, it seems like a not totally unpopular thing to do. Okay, there's a fair bit of that. I guess that's something we could try avoiding. So if it is writable, clone region. Yeah, so that's the fast version, and then I mean, it's not going to be that many regions that happen to be read-only that we turn into cow regions, but apparently we have some, so let's see if it affects our speed at all. Because now I got curious. Seems like not really. At least nothing too crazy. Huh. Yeah. Still, I mean, it seems like a worthwhile thing doing, because the only purpose of this remap is to make sure that the region is no longer writable after making it cal. So don't feel bad about doing it regardless. We got fork, triclone. Remap is still here, yeah, sure. Yeah, I think we'll still bring that commit in, but don't remap already non-writable regions when they become cal. The only purpose of the remap in region triclone is to ensure non-writable page table entries for cal regions. If a region is already non-writable, there is no need to waste time updating page tables. Yeah. Okay, so I think that's going to be it for today's video. So if you made it this far, then I definitely thank you for watching. And I hope that you've seen something interesting today. We certainly got deep in the weeds on some random stuff. But yeah, there's definitely a little improvement here, and it'll be interesting to see how much this affects the CI runner once it is in circulation there. But yeah, it seems like the upper bound here locally at least is something like 10%. Although, as you can see, sometimes these tests take weirdly longer to run. Who knows why? Anyway, thank you very much for hanging out and humoring me while I profile and optimize the SerenityOS kernel. I will see you all next time. So bye-bye.